This guide will teach you how to bake arbitrary water depths into a grayscale Heightmap file for Cities Skylines 1 and 2. The guide will use a Cities Skylines 2 project as demonstration, but the same method can be used for Cities Skylines 1. Your Heightmap project must already be made in Qgis for this to work, so you need to have a complete QGIS project ready for export. It doesn't really matter how you made the project files, as long as you have coordinates for the map extend, or you can get the map extend values from a shape, a print layout, or a GeoTIFF file. Tools you will need: QGIS, open source software. QuickOSM, QGIS plugin. A finished project, made in QGIS. The finished project must be 1 or 2 grayscale GeoTIFF files, in either 32-bit or 16-bit. They must be square and preferable in high resolution, so less than 10-meter resolution. If the file has a resolution of 2 meters or higher, I recommend doing an export of the file with a lower number, for example 1 or 0.5 meter. This is because the water sources will have a very pixelated resolution, as their resolution is defined by your project GeoTIFF file. Our goal: to download polygons and lines of lakes, ponds, rivers, water runs, etc. Converted lines into polygons, so that we only have polygons of our lakes and rivers. Use the polygons as a mask to create a new GeoTIFF file with only water sources. Lower the elevation of those files. Bake them onto our Heightmap. Preparation: you need to have a set of 1 or 2 finished GeoTIFF files, one over the world, optional, and one over the local, playable area. It doesn't really matter if they are not using the right scale in the game. But for reference, the map size in Cities Skylines 1 is 17.28 by 17.28 kilometers, and in Cities Skylines 2, the world map is 57.344 by 57.344 kilometers, and the local map is 14.336 by 14.336 kilometers. The maps in Cities Skylines 2 must have a ratio of 1:4. I will be using the area of my home city, Horsens, Denmark, as demonstration, and the project is made for Cities Skylines 2. I have 2 files that are still in 32-bit GeoTIFF format, 0.4 meter resolution, named 32-bit export, local, and 32-bit export, world. If your files have a lower resolution than 2 meters, generate a virtual raster with a higher resolution. This is important to avoid pixelation. The example displayed is SRTM map data used as world map to generate the rivers. The SRTM has a resolution of 17 by 32 meters, so every generated pixel of the rivers can only be 17 by 32 meters. We simply can't generate a river on a dataset with such poor resolution. Next example is 1.6 meter by 1.6 meter resolution. Here, it looks good, but very narrow bends will not be as perfect as a higher resolution. It will translate over to the final file. But you can also go too low. Generating a river GeoTIFF of a 1 by 1 meter VRT from the SRTM file took well over half an hour for the world map. This image shows the resulting outcome. If we use this to bake onto the VRT version of the SRTM data, we would still get a jagged overall map, but rivers would be nice and smooth. Although the resolution of the original source in a 17 by 32 meter SRTM file, the rivers, and especially the lakes, will. I would even suggest creating a VRT file with map data of 0.4 meter resolution, like I use in this example project, and go with something like 1 meter. I tried directly to generate a river file from the 0.4 meter map. After 45 minutes, it had only finished 5%. So, I skipped it and generated a VRT file of 1 by 1 meter resolution from the 0.4 meter file. That process took 6 minutes. Then generating the river file took 25 minutes. So, what is a VRT? It's a virtual raster file that is easier to work on. Only when you need to generate a file, the work takes longer. If you have a 0.4 meter resolution map and generate a VRT with 1 meter resolution, generating a river GeoTIFF fetches the data from the original file via the VRT, but works on it in 1 meter resolution, instead of 0.4 meter resolution. The sweet spot between having jagged edges and having very long processing time is 1 to 2 meters. You only need to generate a VRT for your world map, as all the work we are going to do is using that file. Only when we want to bake the rivers onto the final files do we use the local file. The easiest way to see the resolution of a file is to right-click it, choose Export, Save As. You can find the resolution a little bit down, under Resolution, Current, Layer. In fact, the export feature is exactly what you should use to generate a VRT. Select Raw Data, check Create VRT, then browse to a folder where you want the VRT. The VRT only needs a path, and we'll use the name of that folder to name the file. So, name the file something that makes sense, like Horson's World, VRT. Set the resolution to a number between 1 and 2. My map only have small rivers of 3 to 10 meters, so I wouldn't go higher than 1.5. Scroll down to Pyramids, and check 1 to 32. This will take a little longer to generate the file, but it basically creates several resolutions in one, so that zooming and panning in QGIS is easy. Click OK. Downloading water sources. First, we need to install QuickOSM. Click Plugins, Manage and Install Plugins. Select all and search for QuickOSM. Install the plugin. You should have a new toolbar available in the top menu. If not, go to View, Toolbars and enable it there. Right-click on an empty space in the Layers menu. Choose Add Group. Rename it to Water Sources. Drag it to the top and select it. Click the green magnifier icon of QuickOSM. In Key, write Natural. In Value, write Coastline. Click on In and select Layer Extend and choose your world map, or if you don't want or have a world map, choose your local map. In my case, I will select 32-bit Export, World. Click Advanced to expand it. Uncheck Points. We are not interested in points of interest, only polygon and line sources. Click on the three little dots next to Directory and choose a destination. My folder structure for a map project looks like this. I will choose my folder, Sea and Water. Choose ESRI shapefile. We will only do one search per query, as the feature to search on several keys and values always fail. This is because there are too many search results and only some sources or none will be downloaded. Now click Run Query. Change coastline to water, and click Run Query again. Continue changing search queries with ease. There are other search queries you can find on the following website, in case you are missing some. Sorting out the files and merging lakes. We now need to group our results into 2 to 4 groups or even more. It depends on how thorough you want to be, but the complexity goes up exponentially the more groups you have. But at least, you need a minimum of 2 groups, one for smaller rivers, waterlines, and one for lakes and larger rivers, polygons. So right-click an empty spot in the Layers menu, and create 2 groups, called waterlines and water polygons. Drag them to the top. Now select all results, with a line icon, in Water Sources, and drag them up in the Waterlines group. Do the same for polygons. Now, click the eye icon on every one of them to hide them. Enable any layer, called something with coastline or that defines something related to the sea. As they are, we can't use them. So, I'll drag them back into Water Sources and hide them. By enabling each layer, one at a time, I can see that my file, place_island also can't be used. So, I'll move it to the original group, Water Sources, for now. Some of the lake files have overlapping polygons. That doesn't matter. Rename all the polygon files so that they all end on polygon. This will make it much easier to select them for our next step. Merge all the files into a shapefile by using Vector, Data Management Tool, Merge Vector Layers. Click the three little dots next to Input Layers and select all files that end on polygon. Click the blue arrow to go back, then set the destination CRS to your project's CRS. At Merged, select Save to File, and save it as a SHP file, shapefile. I will call it Lakes and Rivers. The file contains both, and this is where you might have chosen to separate lakes from larger rivers, if you want a different depth on them, separately. The file contains hundreds of large and small polygons, and as we already saw, some are overlapping. Now, you have the option to delete a lot of small ponds you don't need. If I right-click the new generated file, then choose Open Attribute Table, I can see that the map has over 10,000 water bodies. I don't want to place water sources in all of them, and anyway, we can't put water in water bodies outside the playable area, for now. I will enable my 32-bit export, local file, double-click it, and set the transparency to 20%. Now I can see what area the local file covers and easily delete at least all smaller lakes outside that. Select the Lakes and Rivers file. Click the pencil tool and select Features by freehand. Zoom in and drag around all small lakes in portions by free drawing around them, and then press Delete on your keyboard to remove them. Keep doing this till you are happy. Leave out larger lakes. They might be visible, and someone might give us the option one day to add water in these. After you're done, move to the area of the local file. There can be hundreds of small water bodies here too. But just be aware that even lakes that looks tiny can be quite large. You can use the measure line tool to see how large they are. When you are done, uncheck the pencil icon and say yes to save the changes. Creating a new GeoTIFF file from the lakes layers. We need to create an empty GeoTIFF file with only water bodies of our lakes. If I run the next step on my file, Lakes and Rivers, I will get an error in the log. Error 1, Topology Exception, Side Location Conflict. And the outcome will be a raster with no clipping. We can try and fix that by running the shapefile of our lakes through the tool, Dissolve. Click Vector, Geoprocessing Tools, Dissolve. Make sure the Lakes and Rivers file is selected at Input Source. And at Dissolved, give the new file the name Lakes and Rivers Dissolved. Click Run. Dissolve simply bakes all polygons that are overlapping. This will also give us fewer polygons to cook, as a bonus. The problem is not that there are overlapping polygons, but that one of my files has an incorrect polygon. It can be a polygon with only 2 vector points or a polygon that is open. I know that it's in this case the former, and I know which file is the bogus one, my layer, natural_water polygon. But the function, dissolve, solves this problem. If dissolve doesn't fix these kinds of errors for you and you either get a result with no clipping or just another error that prevents the creation, the only thing to do is to run our next task, clip raster by mask layer on each lake file individually to see which shapefile gives an error. Then simply drop that file and merge the remaining polygon files into a new Lakes and Rivers file. So, let's now run the next task, clip raster by mask layer. Click Raster, Extraction, clip raster by mask layer. Select your world map VRT file as input, and the new Lakes and Rivers Dissolved file as mask layer. Set the target extend to your world VRT file and set the no data value to -9999. Check match the extend of the clipped raster. And check keep resolution of input raster. Set an output file at clipped. Name the file, Lakes and Rivers 0 meter. Click Run. Note that we will only lower the water level on this new file by 4 to 8 meters. If we lowered it more, the import into the map editor in the game might start eating away of the land border of these water bodies. If you want, you could make a new shapefile, then manually draw some of the larger lakes by hand via a polygon tool, then run the new file through, clip raster by mask layer, so that you get an extra file. Then lower the level of that file even more. But it's just quicker, in my opinion, to lower the level in the map editor. Creating rivers from the water lines. We need to do it all over with the rivers on the map that are defined as lines. These lines have no thickness to them, so we need to create some arbitrary fixed widths. First, hide all other layers. By checking and unchecking each shapefile, I can see that the waterway_river has many smaller rivers connected to the rivers on that file. So those rivers should probably be wider than the rest. I can't really see what waterway_basin is covering, so I'll right-click it and open the attribute table. It only contains one water source. Well, turns out, it's a lake. It should have been converted to a polygon, then merged with the other polygons and used in the clipping process we just finished. The same goes for water_lake, but I know that the lakes in this file are covered by the lake polygons. So, we will leave that one out too. The natural_water is also lakes, already covered. I'll delete the 3 files. We won't need them at all. So, this is the remaining result. I will set my waterway_river to a red color, so that the lines are easier to see. I want to get an idea of how wide those rivers are. So I'll use Google Maps satellite imagery to check. This isn't default in QGIS, but you can add it manually. Right-click XYZ tiles, and choose New Connection. Name it Google Maps satellite imagery. And add the following line. Now drag the new Google Maps satellite imagery onto your map, and drag it below all your groups of water sources. Set the opacity to 50%. Zoom in on one of the red rivers and use the measure line to check the width of one of the rivers. Four to 10 meters seems to be the norm. I'll go with a value in between of 7.5 meters. Let's generate a polygon file out of that river. Use Vector, Geoprocessing Tools, Buffer. Make sure the input layer is waterway_river. The distance is a bit tricky. It uses degrees and I can't say if the same numbers works with a different CRS than I use. I haven't tested it. But a value of 0.0001 on my files gives me a width of about 20 meters. I'll use 0.0000375 to get 7.5 meter wide rivers. Name the file, rivers 7.5 meters. Hide that, as well as waterway_river. Checking the other files, I can see the width goes from invisible to around 3 meters. Let's rename them, so that they are easier to merge. Now merge all the buffered files into one shapefile, with Vector, Data Management Tools, Merge Vector Layers. Choose Save to File and name the file. I'll call it Small Rivers. By zooming out and enabling all rivers, I can see there are small rivers that go nowhere. I'll delete them. I'll just do a few here. If we run clip raster by layer mask on this file, we will get an error. We will fix that. Click Vector, Geoprocessing Tools, Dissolve. Make sure the file, Small Rivers, is the input layer. Name the output file, Small Rivers Dissolved. Now, run Vector, Geoprocessing Tools, Buffer, with a set width. I'll choose 4 meters, as most of the smaller rivers I measured off-screen was anything from invisible on the Google Maps satellite images or no more than 3 meters. But 3 meters is a little too narrow. I'll go with 4 meters, so a value of 0.00002. I'll name the file, Rivers 4 meters. We now have our 2 files for rivers ready. Note that the 4-meter rivers, once we generate the TIFF files and bake them into the world map, those tiny rivers won't be wide enough in the map editor. the resolution is simply not high enough. The 7.5-meter river will, but they are barely deep enough. So if you are working on a map with tiny rivers, maybe make a separate file for the world map. If your rivers are more than 10 meters, I don't think you'll have a problem. Just to be sure we don't get any errors for our next step, we will run dissolve on our two files. So, let's now run the next task, clip raster by mask layer. Click raster, extraction, clip raster by mask layer. Select your world map VRT file as input, and the rivers 7.5 meters file as mask layer. Set the target extend to your world VRT file and set the no data value to -9999. Check match the extend of the clipped raster, and check keep resolution of input raster. Set an output file at clipped. Name the file rivers 0 meter. Click run. Now click Change Parameters, and choose the rivers 4 meters as mask. Then scroll down to the clipped, and change the name. Click Run. Creating the sea. We now need to create the sea. First, a bit of cleanup. We have 4 remaining water source files, all covering the sea. Natural_coastline is already covered by the place_island polygon shapefile, so hide that file. And the place_island polyline shapefile is not needed. It's also covered by the other file. Hide that. We now have 2 remaining files. But the natural_coastline is not a polygon file. Let's make a copy to work on. I'll rename it to WIPC. First run, dissolve on the file. Name the file C, dissolved. We now need the tool, Lines to Polygons. Search for that, and open it. Choose the C dissolved file and give it a name, WIPC polygon. Zoom in on the straight line that cuts through the map. Select WIPC polygon and click the pencil tool. Click the vertex tool current layer. Double-click the straight line and drag it outside the area of the world map. Click again. The green crosses you see in a few places are lines on the polygon that overlap each other. Those needs to be fixed. But let's first delete what we don't need. Drag around islands and delete them. The computer is super laggy during this work. Nothing you can do about it. QGIS and the Python scripts running some of our tasks simply don't support multi-core CPUs for most tasks. Only remaining thing to do is to fix the overlapping lines by adding more vertices. double-click, and drag. When you are done, click the pencil icon and say yes to save. Click Vector, Geoprocessing Tool, Difference. Make sure WIPC polygon is the input layer, and select your place_island as your overlay layer. Click Run. Select the new difference layer. Then open Clip Raster by Mask. Select your World Map VRT as input layer. Set the target extend to your World VRT file and set the no data value to -9999. Check, match the extent of the clipped raster, and check, keep resolution of input raster. Set an output file at clipped. Name the file C0 m. Click Run. We are now finally done with all our files, and can start on the fun part. Lowering the water level on the files. We can now lower the water level on our 4 GeoTIFF files. I'll lower the water on the small rivers, the file called smallrivers-0m, by 4 meters. 7 meters on the rivers, the file called rivers-0m. 8 meters on the lakes and rivers, the file called lakes-and-rivers-0m. And finally 8 meters on my sea file, called sea-0m. Click Raster. Raster Calculator. Double-click Small Rivers 0m at 1. In the raster calculator, the field now says Rivers at 1. We can now add a calculation that lowers the water level of the file. I'll add -4. In the output layer, I'll create a new file. Called Small Rivers -4m. GeoTIFF should be the output format. Click OK. This will take a while. Now do the same for the other files. Baking the files. A fair warning. This last process will eat a lot of hard disk space. My 4 files plus the world map are over 110 gigabytes together. All these files need to be read and put in a temp folder on your C drive. It will easily eat 60 gigabytes or more. And if your files, like mine, are on a traditional hard disk, like the 16 terabyte drive I'm using here, it will take a long time just to load the files. We can now finally bake all our files together. Our world map and the 4 files we just generated. We need a tool called r.patch. We need to look it up in the processing toolbar. There are 2 tools called r.patch. You'll have to open them one by one to find the right one. It should have the option to choose several files. The very first text should say raster layers to be patched together. Click the 3 little dots next to that text. The order here is important. Your world map should be last, then the others, right above. As some of my rivers cut through my lakes, and the water level there is lower, I will drag C-8M to the top. Then lakes and rivers -8M, then rivers -7M, and lastly small rivers -4M as the fourth. Below that, my Horsens World VRT file. This does that the files take priority from the top to bottom. Click the little blue arrow. Set GrassGIS 7 region extend to your world map. Next step is important. At Output Rasters Format Options, write BigTIFF equals yes. This will force BigTIFF format that supports files greater than 4 terabytes. Scroll down to Patched and give your file a name and destination. I'll name my file Horsens World Final. Now click Run. It will take a while. I'll also run the local file through the same process. Same order of the files, except change Horsens World VRT to your local file. Also remember to change your map extend to the local file. Set GrassGIS to your local map. I'll name the output file Horsens Local Final. Exporting the files. Final thing is to translate the final files to a format the city Skylines map editor can use. We also need to raise the overall water level. I know that the minimum level of the files in meters is around -9 meters. So, we need to make room for the water. I'll raise the level by 200 meters. Click Raster. Conversion, Translate. Convert Format. Choose your first file, in my case Horson's World Final, as input layer. Choose the correct CRS. Set profile to no compression. At additional command line parameters, I'll use this line, as I want my whole elevation raised by 200 meters. My guide on how to create maps for cities Skylines 2 will explain all about these parameters. Under Output Data Type, choose uint16. Under Converted, name your file and destination. I'll name mine Horson's World plus 200M. Click Run. Click Change Parameters, scroll to the top, and select your local file, in my case, Horson's Local Final. Scroll down to Converted, and change the name. Click Run.